Hey folks, I decided to piece together the entire 7-part series on solar climate forcing from 2020. It is true, we have had many updates and confirmations of the science since then, about 185 papers to be exact. But the mechanisms, the forcing pathways, and the concepts remain true. I hope you enjoy. I'm the author of the textbook Weatherman's Guide to the Sun. I also have peer reviewed papers on solar terrestrial physics, and right now, I am 100% devoted to making the seemingly complex topic of solar forcing of the terrestrial climate as absolutely simple for you to understand as possible. If you have been following here, and the climate science the mainstream media seems to be refusing to cover, then 2019 was an interesting year. Following bombshells in 2018 from Princeton regarding the cooling potential of clouds, which makes us think about our cosmic ray cloud inducing future, and from Yale regarding the cold climate bomb waiting to be unleashed by the Arctic, 2019 saw hundreds of university researchers breaking stride from the mainstream narrative on man made global warming. Some of the more notable ones were from Harvard, which jumped in on both the oceans and the atmosphere. The American Geophysical Union devoted an enormous amount of time to significant solar climate forcing at their fall meeting. It was a quasi-taboo topic just a few years ago. We heard the World Meteorological Organization, which is the daddy of the IPCC, condemn the climate extremism as being factually wrong, unscientific, akin to religious extremism, and bordering on terrorism. The basis of the lack of factual correctness comes with confusion between scenarios and predictions. The IPCC does not do the latter, and in fact says it is impossible, something NASA's guidelines say as well. Too many moving parts we just don't understand. And all of this comes ahead of the 2022 major IPCC climate report. It will be the first one ever to account for solar particle forcing and cosmic rays. Here today, we are going to explain to you what's happening in the climate game, especially since the news won't seem to report it. We'll show you why this was a necessary change made by the IPCC and the rationale behind the change. Then, we are going to examine what's still missing and the exact roadmap for mainstream climate science to cross the finish line. Let's begin with carbon dioxide. This is changing due to human activity and natural variability to the tune of parts per million. Now, this tiny fraction has long been believed to have great power over the climate due to a number of closed system experiments done in the lab in the past. But these don't mimic the Earth, as this is not at all a closed system. Ergo, the recent IPCC changes. Moving up to solar irradiance, the light of the sun. It changes by 0.1% or by the thousandths over the 11-year sunspot cycle. This is still 100 to 1,000 times greater variability than what we're seeing with carbon dioxide, but somehow still comes up short in the models. Well, now fast forward to today, and we're forgetting the fractions because what's going into the models into the future is going up by orders of magnitude when it comes to particle variation, and we are still to this day discovering exactly how these particles are interacting with aerosols in the atmosphere, how they affect atmospheric electricity, and cloud formation. The first aspect of this is cosmic rays, and in this, they are indeed making incredible strides. Cosmic rays come from tremendous space phenomena like supernova or cosmic jets. They often come from galaxies far away and still arrive with tremendous energy. Unlike photons like gamma rays, which are in the central column, cosmic rays are atomic nuclei, high-energy protons or heavier atoms with their electrons stripped. You see them over to the sides. These create incredible particle cascades of the subatomic nature, not to mention their own gamma-ray photons. Cosmic rays cause cooling of the Earth and ionization of the atmosphere. And just picture this, given those particle cascades. Clouds form as water droplets and dust and other aerosols come together. The cosmic ray particles are deposited into the atmosphere, neutralizing or attaching to dust and becoming cloud condensation nuclei. They also strike other particles and ionize them, making them more attractive to dust and water vapor by the same static attraction force that works like a Swiffer duster in your home. The sun's activity directly controls how many cosmic rays enter the inner solar system, and so cosmic rays rise and fall opposite of the solar activity cycle, which has been reported in numerous cloud datasets. Of course, the sun itself is the primary producer of particle interaction with the Earth, Some particles sneak past Earth's magnetic field along the interplanetary magnetic field lines, but most is in the form of the solar wind and its interaction with Earth's magnetic field. Its heating of the atmosphere, its modulation of the global electric circuit. This is the process still to be officially understood and recognized by even those introducing the particle forcing into the equation today. Earth has a mini version of the solar wind. It comes from two places. First is the equator, the equatorial ion fountain, an ion release from the upper ionosphere that is not strong enough to escape like the sun's solar wind. In fact, the lowest L shells and Van Allen belts nicely contain them, forcing them back down into the atmospheric circuit. It's actually not exactly at the equator, but at the magnetic equator. And the other place it comes out is at the poles, just like you see with cosmic jets from newborn stars, active galaxies, and quasars. It's called the polar wind or polar ion wind, and this actually can escape, mostly along Earth's magnetic fields, at which point it is blown back by the solar wind, either into the reaches of deep space or back into the circuit on the midnight side of the system. Now, for the simplest way to demonstrate how this process affects the atmosphere, imagine a strong solar flare releases a coronal mass ejection, which strikes Earth's magnetic field, some of which gets directly integrated into Earth's magnetic field and then down into the atmosphere, and the charged particles block out cosmic rays, and indeed we see cloud levels thin and coverage percentage drop during these impacts. But also there is the strong compression of the magnetic field and the redirection of both the ion fountain and Van Allen electrons down into the atmosphere, combining with the particles deposited there by the magnetic field integration, and here is what happens. We now have more electric particles in the same size circuit of the atmosphere. Well, smaller actually because one side of it is compressed. And also, the solar energetic particles coming with the large flares also add to that mix. And the atmospheric global electric circuit is now the recipient of those particles. And stronger current means stronger downflow and high pressure, stronger upflow and low pressure, driving pressure differentials, intensification, increased storm activity, and atmospheric heating due to the direct particle interactions, and induced current ohmic heating through Earth's resistive atmosphere. So in one CME event, we have lower cloud cover and therefore lower cooling, increased electric heating and direct particle heating, intensification of the weather, and folks, this is what shows up in the climate record. Not joking. This was a huge point in our climate forcing movie, which is linked below and a must-watch if you are interested in this topic, and this occurs because the sun's energy scales up from ultraviolet to X-rays in the large solar flares. This is more absorbed in the ionosphere than in the upper atmosphere, which is where they gauge solar forcing. And because the giant plasma cloud CME blocks out a tiny fraction of the light, we also get this dip. They're working together to create this drop in the apparent solar forcing. So, while the sun's input to Earth is actually jumping 10 to 10,000 times, or in some cases, 100,000 times or more, there shows up a tiny drop in solar energy in the climate models. This drastic problem, pointed out during the early stages of the last sunspot maximum in 2012 and 2013, was finally rectified in 2017 when the official particle dataset was released to the community. This problem right here is why they're making the changes. While so far, nobody has been able to publish a study showing massive human contribution or catastrophic future warming while using these new datasets, the people who are publishing are doing so at the highest levels and in the highest forums of geophysics. This is why this chart is so critical. The 1900s saw the greatest solar activity, according to 3 different isotope records, since the high activity that ended the last ice age. The grand solar cycle is set to bring less CMEs, more cosmic rays, and a vastly different external energy environment for our planet for the rest of the century, with magnetic activity already indicating that this may be the last proper sunspot cycle coming before the plunge into grand minimum. There's more to come on why the climate game is inches away from changing forever. Be safe, everyone. In Part 1, we showed the changes being made in the climate game by the IPCC, the reasons, the rationale, and support for those changes by NASA and top universities, and we showed why it is so important that the drastic elements that have been previously missed in the equation are now coming in. We discussed the different ways that cosmic particles affect the planet, and we began to describe the mechanisms of action. But there are considerable details to those interactions, and unfortunately, they are not so nice and easy as the cosmic ray penetration and electric particle cascade. For the solar wind, the path to the atmosphere is somewhat more complicated. This is Part 2. When the sun unleashes a solar flare and coronal mass ejection of plasma, it intensifies the solar wind, and also surges high-energy protons to Earth along the interplanetary magnetic field. But once these sneak past Earth's magnetic field along that connection, what happens? How does it integrate with the system? And what about that solar wind? The daily flow and the stronger CMEs. It's not exactly as simple as the compressed sun-facing side of the field sends down particles, and it is very different than the plasma penetration at the cusps, where the Birkeland current sheets can help guide the plasma into the auroral zones, where it creates the pretty northern lights. As a matter of fact, there are two other things at play here that are critical to understand. While the magnetic field blocks and deflects some solar wind, some is integrated with it directly and is carried along the magnetic fields, which in the case of the lower L-shell field arcs, interacts not with the poles, but with the parts of the world in which we live, almost down to the equator. Well, when we get hit with a CME and a geomagnetic storm occurs, they notice reverberations in the field down to ground level, with VLF and ELF emissions. Recall that it is not the actual field reverberating, but it's actually the electrons caught in the field that produce that low-level electromagnetic radiation, and the extra electrons and energy levels to create those emissions are a critical sign that the actual field of Earth itself is one of the pathways to the atmosphere for those electric particles, and none of those electric interactions with the atmosphere are currently in the climate models. This topic can be easily investigated with internet searches for geomagnetic storm, ELF, or VLF, including how they think some of the human health correlations with geomagnetic storms are indeed due to those low-frequency emissions. They are getting very good at tracking the evolution of those emissions over the evolution of the geomagnetic storms, and frankly, they should be. They've had 60 years of studying it, and by the way, back when they first discovered it, even in the 60s, they fully understood how these processes contribute to atmospheric heating. What happened to have this lost from climate science and models since then, I really don't know. But we're moving on. It's the second of the pathways, and this one is a bit more complex. We described the extra particle injection, and you could probably imagine how the compressed field pushes down on the equatorial ion fountain and intensifies the circuit. More electric particles, smaller compressed circuit. That's high school logic there. But to get us from there to here is a somewhat more complex story. How the solar wind ends up affecting surface pressure, air temperature, ocean temperature, and convective atmospheric potential energy, the large-scale oscillations and modes in cells. And the answer lies in between the large-scale magnetic field of Earth and the lower atmosphere through which the primary circuit runs. It's called the ionosphere, which is the ceiling of this circuit, with cloud layers, the ground, and even the mantle acting as various floors for the circuit. And that ionosphere is another shell-like structure wrapping around the planet, sitting atop the atmosphere. It is comprised of mostly ionized or electric particles, and it is segmented into these shell layers around the planet. For those who know about electric fields, these are indeed current sheet double layers. In recent years, they have detected up to the F4 layer of the ionosphere, which some are taking to mean that Earth's magnetic field has crossed a major boundary in its current weakening, but more important than how many shells we have is what they tell us about the external environment interaction with our planet. And we're off to the Sapphire Project. Little shout out to their administrative lead, Montgomery Childs, who is a great friend of mine and a great guy to know. In case you couldn't tell from the images here where they're turning up the juice, these electric current sheet double-layer shells form naturally around a planet like ours in a similar space environment where tremendous induction is sustained from the solar plasma flow. Now, what's going to be key here is for you to think about this in reverse. This is all about plasma pressure. When one shell gets too energized here, another bleeds out around it. Well, this can happen in reverse if the shells exist and something like a CME hits it from the outside. The outer shells would take the energy first, gain plasma pressure, and with it, stronger from the outside, the energy has to bleed inward, down and down, shell by shell, based on how much energy is coming in from the outside. And this is actually a fairly slow process compared to the magnetic field reverberations, which can happen instantly upon impact. There is buildup time on the plasma density, and while we do indeed see Van Allen electrons shooting straight down through the shells and atmosphere in these impacts, the vast majority of what affects the pressure column is running in that shell system and is based on plasma pressure. And when it finally gets down through all the layers of the ionosphere, which basically stop at or just above the ozone, where high-pressure cells sit beneath, there is a nice pathway to the ground. Indeed, we see the air descending through high-pressure cells from the jet levels or higher. The different floors capacitize and accumulate, then discharge upwards in lightning, general low-pressure cell circulation airflow upward, and even volcanoes and earthquakes. When the ceiling takes that energy from the outside, the effects on the ground can be fairly rapid, not quite as rapid as the magnetic field reverberations, but in polar regions, they do note changes in cloud cover and surface pressure in as little as 10 minutes after the change in the solar wind. The entire circuit ramps up because it's all part of a system. Think about a belt in your car. Not the whole belt is touching the spinning wheels at all times, but the whole thing moves together because it's a connected circuit. While the global electric circuit intensification and pressure and cloud modulation are being recognized and modeled generally, there is very much work to do on the fine detail of the ionospheric interactions, and also on the kinetic and ohmic heating or Joule heating effects of the electric particles, whether their path to the atmosphere is fast on the field or a crowded stampede down flights of imaginary stairs. More videos coming. Be safe, everyone. In this examination of solar modulation of the jet streams in polar vortices, we will be expanding on the lessons from parts 1 and 2 on the plasma particle influence and their path to the atmosphere. The goal here is to provide 2 macro-scale facts from the peer-reviewed literature, some sources that you can pause the video and jot down if you need to dive deeper, and then show the mechanisms behind these atmospheric modulations. The first key fact is that solar minimum brings more jet stream blocking. Solar maximum brings fewer of such events, and jet stream blocking is how you get considerable exacerbation of drought or flooding, and how you go from 10 degrees above average one day to major storms that night, and 10 degrees below average in the days that follow. Solar minimum also brings more polar vortex weakening events. Solar maximum brings far fewer, and for most parts of the world, the weaker the vortex, the worse the winter cold will be. One of the major exceptions to that is Australia, which tends to see hotter and drier conditions due to where the southern vortex tends to kink. Now, in terms of how the sun does these two things, we're going to go through these items here and describe how they work. First, up top, we do indeed see about a 10 meters per second difference in the upper jet speed between sunspot maximum and sunspot minimum, with the jets being faster in the maximum. Now, while the jets are not quite up at the ionospheric level, there is a vastly greater interaction and coupling with the D region of the ionosphere, and much greater access to the sunlight and solar particles, especially than, say, at ground level. And one contributing factor is indeed the increased ionization and heating of the upper atmosphere by solar flares, which of course are much more common in sunspot maximum. The second point notes that high solar activity also pushes the jets towards the poles, all while expanding the Walker cells. Now we're going to hold on to why regarding the jets moving towards the poles and look at the Walker circulation, which is an equatorial beltway, which involves El Nino and La Nina, which by the way are also shown to be heavily influenced by solar activity, and the expansion of these Walker equatorial cells due to solar heating is really one of the keys to all of this jet and vortex forcing. Because in the third point, we see that the Hadley cells are not only expanded like the Walker cells, but they too are pushed poleward in terms of the other atmospheric cells. So there's no way to put the Walker circulation on here too, except for plugging this little overlay on, and this is what's causing the rotation to also spin in the Hadley cells in that vortex, helix, spiral shape around the globe as opposed to spinning in space. So picture the Walker circulation with the Hadley cells there in the equatorial region. And now look at the sunlight exposure, the CME compression exposure of the magnetic field, where the Van Allen belt electrons are pushed into the atmosphere, and compare what's going to happen at the tropics to the rest of the world. It's no wonder we see the primary expansion of those tropical cells and circulations when the sun is giving them more to work with, which naturally pushes the jets towards the poles as the cells expand, since the jets ride between the Hadley and Ferrel and polar cells. And so yes, when the equatorial cells are puffed up and the jets themselves are getting more energy, they are faster and tighter and pushed away from the equator to hold the polar air firmly at the polar region. Those events where you get snow coming down to the southern parts of the Gulf states doesn't happen without the jet stream or polar vortex, or likely both, being too weak, too wobbly, and failing to confine the polar air, as the equatorial cells are likely deflating and allowing everything else to come towards the equator and sunspot minimum. With the polar vortex, there is also that forcing of the direct particle interactions from the magnetic field, which does couple particles directly to that region, which is also why Australia is one of the oddballs in weak polar vortex events as they get heat and drought. The South Magnetic Pole is actually near them as it has left Antarctica, and so the vortex tends to dip the other direction away from them. If it seems like the how of the solar energizing, heating, and expanding of those equatorial cells was somewhat undercovered in this episode 3, there's a good chance you missed the first two regarding cloud microphysics, sunlight access, and particle forcing by Joule heating, among other mechanisms. Both of those examinations are linked below this video. In case you missed them, they will be very helpful for this one. And so to review, that solar forcing takes its most effect at the equator, at least in terms of large-scale cells in the atmosphere, Walker and Hadley, more than the Ferrel and polar cells. The cell expansion at the tropics pushes the jets and other cells towards the poles, where their more energetic state at sunspot maximum is now in a better position to confine the polar air and avoid the jet stream blocking that creates the weather extremes. It really is that simple, and yet its understanding in academic terms is still relatively new. It will be a major factor in climate science moving into the future. We've got more coming in this series, and whenever you're watching this, I'll be here in the morning for the daily update. Be safe, everyone. The plot thickens. Top scientists and organizations are changing the game. The news won't report any of it. The journals are caught in the middle, in the wake of a tsunami of studies on solar plasma climate forcing. We've shown the particle dominance in the energy delivery, their paths to the atmosphere, and the effects on the vortex and jet streams. Now, it's time for the oceans. This Part 4 has two parts itself: the review of one of the most robust and recognized solar forcing correlations, and the introduction to how the Earth has hidden the solar effect, and a man who may be ready with the right idea at the right time. We begin with ENSO, the El Niño Southern Oscillation, El Niño and La Niña. This is one of the most studied and most verified solar forcing manifestations, and this one was actually recognized well before the recent shift to allow solar particle forcing into the game, but yet it still lacks a place in the models. By the way, there are more citations listed in this video here in case you are the pause, jot down, and dig deeper type. It is a direct correlation. High solar activity pushes ENSO positive towards El Niño, while low solar activity pushes ENSO negative towards La Niña. It's not so dominant that it overtakes the natural cycle, but if we were supposed to have an El Niño, high solar activity would intensify it. If it was supposed to be a La Niña cycle, then sunspot minimum periods would intensify that. They are noticing that both 2 and 10-year lags in the forcing exist, and this is actually a very common lag period when it comes to the solar forcing of the terrestrial climate. While some particle forcing does manifest within minutes. Others have lag times of up to 20 or 30 years. This just means that the oceans are taking in the heat and holding onto it or pushing it deeper to where it slowly can bleed back out into the atmosphere. Now, when it comes to how the sun injects that energy into the oceans, the pathways are the ones we already know. First, it's the cloud cover and sunlight exposure factor. Sunspot minimum, with more cosmic rays and more clouds, allows less light into the oceans, while solar maximum has the opposite effect, plus a tiny bit more ultraviolet light on those sunny days. Now, think about how far down into the ocean you'd have to go before the water is pitch black. Everything above there is taking in sunlight, directly transforming it to heat and cycling it around in the oceans. That's before you ever consider the particle forcing. And then we have to also consider those large-scale circulations that we looked at in Part 3, when the Hadley and Walker cells take in not only more sunlight from the lower cloud cover and sunspot maximum, but the majority of the particle forcing from CME impacts as well. They present one of the key drivers of not only how much energy can go into the oceans, but how much can come back out. Now, when it comes to the studies of the sun and direct effects on sea surface temperature, they are very numerous, but show only a small effect in real time. The process doesn't really seem to kick in for 1 to 3 years later, with cycle modulation rather than intensity modulation on the decadal scale. We have seen studies of deep ocean temperature relatively well confirm that the deep ocean lag can stretch to that 20 or 30 years, which, by the way, is everything you need to explain why the global warming pause started almost a decade after the peak solar flux to Earth, and why Earth won't really start to cool down until a few years after the grand minimum begins later this century. But what if you could stretch these lag periods to, say, 75 or 85 years? That's when you start to see CO2 dropping below the relevance mark almost altogether. For studies of this length, you can't go with climate scientists. You need someone focused not on the atmosphere, but on the broader scope of geophysics. I've got a list of some scary outcome and solar forcing research by a Roger Higgs, PhD, sedimentology. Oxford, for those Americans who don't know, it's consistently in the top 5 of the world. It took about 2 minutes of me checking into this guy to find the sort of writing indicative of master-level understanding. Telling the difference between long-period accumulation and rapid deposition in sediments is not easy. And furthermore, when someone lists their rejected papers alongside their accepted ones, there's a lot to be said for the character there. I could challenge you to go find many professors' pages that meet that standard, and you will fail that challenge. So his listings are under an umbrella project that addresses a massive, non-human caused sea level surge ongoing, and to do so he must first demonstrate the real long-term driver of climate change. There would be no way for me to go over all of his slides and conclusions, but they can be described as a nearly overkill proof that the sun not only has that 20-year lag effect in the oceans, which he clearly identifies, but also a much longer 75 to 85-year lag. Heat is quickly circulated into the depths of the water, but there it can continue to circulate or disperse and wait to present itself at the atmosphere once again. He also demonstrates that before the Industrial Revolution, an increase in CO2, plants were rapidly approaching their starvation point in the atmosphere. This is a point that was made by other scientists, one in a presentation you may have heard called a dearth of carbon. We are actually approaching, but not yet arrived at, the optimum level of CO2 for plants, the level where all great life explosions in Earth's history have taken place. He touches on a point that we have made many times, that the grand solar maximum of the last century is the real cause of global warming. He correctly identifies it as the strongest of the last 1,000 years, and observers, you should remember that Ussoskin has pretty convincingly showed it's likely the strongest in 12,000 years. About the only thing I could ever disagree with is the potential time frame for Higgs cooling, which he says is still decades away, with the 85-year lag after grand solar maximum. But the slow heating is a little different than Svensmark's cosmic ray and cloud processes. The atmosphere reacts much more quickly, and those don't need much time at all. The key point here, of course, is that the oceans are indeed a thermal trap, and they forbid nice and easy real-time correlations between solar activity and the temperature of the atmosphere. The 20-year lag from the oceans means we are still seeing the heat from the grand solar maximum today, right now, and I do have to say, This longer cycle has a lot of evidence and may be the last piece of the puzzle in explaining the recent warmer atmosphere of the planet. Now, one of Roger's best pieces in the project turned out to be a bit of an assault to read on the phone, so I've copied it into a public Word document for you. This is his work. I'm merely reposting it here with a link to the original. The 27 points in the short work offer many more talking points, questions, and doubts on the story we've all been fed for so long. Folks, as you can see, even with the much greater particle forcing now allowed into the game after 40 years of climate science stiff-arming astrophysics, there are still so many subtleties, nuances, and long-term modulations of the effects we see. The sun's energy has a few paths to the atmosphere, but once it gets there, it's got a smorgasbord of choices and pathways and hiding spots and circulations, and it chooses them all. So to review, there have been enough irradiance correlations with climate ignored to create the question that has plagued climate science for decades. The particle forcing now allows the rest of the major energy budget to be reconciled, while the oceans mask the correlations and lag its effects over many years. In Part 5, we will be getting into the other side of this scale, the more immediate effects of solar activity, and that's when things actually get terrifying, not only for those who are affected, but for those who have spent their lives taking our money to deliver a biased conclusion based on a half-truth. Be safe, everyone. The solar forcing we've investigated in the modulation of large-scale cells, modes, and circulations, of cloud cover and temperatures and lightning and precipitation, does not fail to affect the most devastating of the weather phenomena: tropical storms, hurricanes, typhoons, and cyclones. I do wish climate scientists realized what they know now back in 2014 when this paper was published. While the normal ambient geomagnetic variations do show electric forcing of the lower atmosphere temperature, the Joule heating, they suggest a small role played by solar irradiance, implying but not driving home on the point of particle forcing. And their analysis revealed a more extreme story when it came to the geomagnetic storms. We know that irradiance doesn't change much in those either. It's all about the particles. Oh, if only they had gone one step further in 2015 when they solidified the 22-year cycle of tropical cyclone activity, same as the magnetic cycle of the sun. They, too, failed to prove how solar irradiance could muster such a correlation. Of course, the answer there is the particles, too. The rookie in the game, the new guy in town in terms of climate science. We're going to review some real-world correlated events from our past conferences, discuss the happenings since then and their tie to solar activity, look at the more recent research propelling this field forward. This is the relevant portion of our 2015 conference presentation as it appeared in the full movie.
And so let's take a look at what happens when the sun fires off and when the sun affects Earth in terms of the tropical activity. The KP8, the level 4 geomagnetic storm of this summer, was followed just days later by 6 cyclones popping up in the Pacific. In 2013, we had an X-class flare and magnetic crochet, and just days later we have Typhoon Haiyan. Every single one of those big-time typhoon records are held by either Haiyan or Typhoon Tip, which occurred in October at the exact peak of sunspot activity back in 1979. So, can you guys all see the timestamp down there? Is that sticking out to you guys at all? So we had very, very quiet space weather actually for days and days and days. And then, all of a sudden, the sun woke up. But these were the type of tight, coiled CMEs that you often see really perturbing the inner heliosphere. And of course, this occurred, as I heard somebody say, exactly at the start of Hurricane Katrina. The last time we had an X10 solar flare or higher was just a few days after that event that caused Katrina, and that was an X17. And the mid-month storm outbreak was the very last time before this summer that we had 5 Pacific cyclones at the exact same time. The last time we had a near major solar flare was an X9 in 2006. We had the Hanukkah Eve cyclone strike Washington. And to set a rain record in Seattle is no small feat.
That full presentation back in 2015 covered many more events, but now let's jump to September 2017 once again. This was the next time the sun got really active after 2015, and it was an unexpected flurry amidst months of quiet. But it surged X-rays, high-energy proton radiation storms, intense solar wind impacts, and tremendous geomagnetic storm activity. When the first sunspot appeared, Hurricane Harvey ran ashore in Texas, and by the time the major flares were occurring, the hurricanes were surging as well. Irma, Maria, Puerto Rico devastated. Panhandle and Georgia hit hard. It was the last great solar uptick we have had, and in 2019 thus far, the sun has been tremendously inactive, but it is showing signs of coming back to life for another sunspot cycle maximum, set to gear up in the next few months. Okay, flashback over, and we're back to part 5 of this follow-up series to the movie. Since 2017, the only solid, strong geomagnetic storm we've had came in August of 2018, just as Hurricane Florence was gathering for its run across the Atlantic. While the sun has been quiet here recently, the scientists have not been. While research continued to show modulation of the large-scale cells, modes, and circulations of cloud cover and temperatures and lightning and precipitation, the research demonstrating that space weather affects tropical storms and cyclones has continued as well, including an investigation of that 2017 outburst, although I must say I'm confident that our textbook shows it extended to Hurricane Maria as well. The mechanism of focus appears to be on the rapid pressure changes at the surface, something demonstrated in non-tropical storm situations by numerous works in the peer-reviewed literature. The same premise of particle forcing on the global electric circuit and the larger cells themselves, not to mention on cloud microphysics, affects the pressure cells from weak to ultra-powerful in the same mechanisms we've investigated in Part 2, Path to the Atmosphere. It's literally the same thing, just applied to the pressure cells that tend to make the news, even if the particle efforts in that application do not. Hopefully you can see we're now building upon the previous episodes. There is more to come. Be safe, everyone. We've come to what will inevitably matter in climate discussions more than anything else. More than storm forcing, problems with models, and more than 1 year, 3 year, 20 or 85-year lags in the atmosphere and ocean. It's the rapid temperature forcing of the extremes of solar activity. Now, on the lower end of the scale, we've already looked at the strength of the jets and the inflation of the large-scale cells and how it diminishes quickly in sunspot minimum, as clouds are increasing due to the cosmic ray nucleation. But now it's time for the other extreme, and the immediate temperature forcing in the direction of heat. We go to one of the first papers on solar proton forcing in what I'll call the new climate era, the era of particle forcing, which began with Mathis et al. In 2017 when the particle forcing dataset was released. Now, this paper by 2 Harvard professors explored how bad things on Earth could become due to a superflare on the sun. And in the course of ultimately finding our planet to be at extreme risk over the long run, it confirmed that extreme solar events can create rapid heating events in the atmosphere. Now, while studies on these short-term forcings due to solar protons are rare, 2 excellent cases indicate warming events that took weeks to bleed out of the lower atmosphere, after which it went into the oceans or upper atmospheric layers where it has the potential to lag later. And it makes the global warming we hear about on the news seem like small potatoes by comparison. Some studies have sought to tie these changes to UV forcing alone, the solar irradiance, implicating incredible depletions of the ozone. Now, while detections of such atmospheric chemistry do linger for weeks, the full accounting of the heating that is observed cannot come without solar wind particle precipitation. It was a move seen as bold and outside the norm at the time. Not so much anymore, with those particles officially allowed in the IPCC climate models. By the way, the zonal and vertical winds were also noted to have changed considerably in the 2003 event, implying those particle forcings of the global electric circuit, the total atmospheric column, the Hadley and Walker cells, and the jets. Again, the new player in the game. Now, it's important to know that the rapid heating from extreme events is very different than the heating or cooling you get with the 11-year sunspot cycle. This has different effects around the globe, with solar maximum usually bringing heat but still bringing cold to some areas, and while solar minimum usually brings cold, it does bring heat to some areas. And outside of those most extreme storms, the 11-year cycle forcing we're looking at is on the large-scale oscillations in the Atlantic and the Pacific, things like the AMO, PDO, El Nino, NAO. These also do cause localized regions to experience the opposite trends of what the rest of the world is seeing. We know that with those oscillations now. It's just a strengthening of them we get from the sun. An example of cold coming with solar maximum is found in southern China, where precipitation increases in late winter due to those large-scale forcings, including on the Asian monsoon and the jet stream, and they add snow and a bit of albedo forcing to the region to sprinkle some extra chill on their sunspot maximum winter's end. Of course, on the whole, the studies that exist do show the statistical correlation in most parts of the world as direct: heating with solar maximum, cooling with solar minimum, although how much of that can be attributed to those large-scale modulations and how much to direct particle forcing, especially in those extreme events, remains a mystery. Those hundreds of studies throughout the years have succeeded in presenting the correlation and getting published, but always fell short of both proving how ultraviolet light could account for this forcing and of making their way into the official climate models. Perhaps the former is the cause of the latter. Of course, now that they are allowed in the VIP, they're bringing a few friends with them. To be honest, I always thought the missing piece of the puzzle would be found by proving Joule heating from the protons and electrons, and then it would be forced to come into the models. Right now, the ozone effect and the atmospheric chemistry are the reason they're there. They are the main course that they're going to take in this first experience they have with the IPCC, but now that they are allowed in the models, it is up to the scientists to use their new tools to adjust attribution modeling of those forcings. Again, they are allowed in the game, but are still somewhat handcuffed in the models, with the full ohmic dynamics and global electric circuit left unsure they'll get called onto the field at all this next round. Now, as it is, this will still produce a measurable attribution change in the modeling, but the full realization of solar plasma climate forcing will not come until the full effect of solar protons, Van Allen electrons, and the excitations of the Earth's magnetic field and atmospheric electricity are fully understood. These Harvard professors tried to do two things on the heels of the official release of the solar particle dataset. They wanted to draw attention to the potential cataclysm that will unfold when the sun shifts into that rare sixth gear again, but also they wanted to express the multi-degree, short-term particle forcing that is not only missing from the models, but if we recall from episode 1 of this series and from the full movie, they blame that forcing on humans because for all the extra input of energy and excitation of the Earth's existing energetic systems, the models show negative solar forcing in the irradiance data during the most extreme events. And as a reminder, that means that the real solar effect is not attributed properly. The real climate effects are blamed on human forcing, and since there is actually a tiny and false data drop registered, they actually tick the human forcing up a bit higher to account for it. These events heat the world, and it counts as human forcing plus whipped cream on top. Let's remember, the period of global warming in the second half of the 1900s saw twice the CMEs as the prior period and the last 20 years. This is a tremendous amount of solar forcing that is unaccounted for. and blamed on humans. We are nearing the end of the atmospheric lag from the grand solar maximum of the entire Holocene. There is still oceanic lag to go, which will manifest as strong El Niño releases of that heat into the atmosphere, but also will help melt water in the North and South Atlantic to chill and desalinate the sea and begin the trend the other way. All series episodes are linked below, along with the full movie. We update the sun, earth, and science news relating to this and important other topics 365 days a year, right here. I'll see you in the morning. Be safe, everyone.
The global electric circuit has been known, since even before the time of Benjamin Franklin did his experiments on thunderstorms and also in fair weather. You can fly a kite in fair weather and it'll cause electric discharge if you have a conductor coming down from the kite.
Part review, part criticism, part correction, part progress, and part outlook. We're about to be caught up on the science and societal posturing as we enter the new era of solar forcing climatology. When you realize that you have to go down over 600 feet into the oceans before the sunlight can reach the depths no more, and that all that light is directly transformed into heat, it isn't necessarily difficult to see how that heat can be lost for years in the ocean depths, or how extra particle-driven forcing might be able to do the same. But wrapping your head around the million-year near carbon dioxide starvation of plants, and that greenhouses keep levels at least 3 times higher than in the ambient atmosphere today, the complexity of the concepts accelerate. So, we learn to lean on foundations that are easier to construct, ones that demonstrate critical flaws in climate models, the true variability of our star's energetic deliveries to Earth, and the perspective on plant food measured in parts per million. Even in the lower variability aspects, like the multi% spikes in neutron counts during major solar outbursts, which can still be 100 times or more variability than the solar irradiance at 0.1%. There are many problems in the models that have caused the UN to change the game looking forward to 2022 and beyond, and indeed, in the meantime, the anthropogenic blaming crowd is holding on for dear life. The sad thing is that this is a reputable academic website, and these are not climate scientists, but a space scientist and a physicist, and both should know better than to use sunspot data in these comparisons to temperature data, which is going to confound and further trick their readers of, again, this reputable academic website. Now, since these authors decided to be lazy and pandering, and since their fields demand better diligence of them, I've decided to use them to demonstrate how you can easily debunk articles like this until the larger story begins to change. And considering the slow crawl of academia, that could be a while, and so you'll need this skill. The core description accompanying those charts, which we'll see again in a moment, is this, and their first paragraph is utterly accurate. Cycle 24 was one of the stepping stones down towards the grand solar minimum expected this century. But in the next paragraph, they make their first move of what is hopefully honest ignorance. Their application of a direct time frame forcing to the sun is not at all accurate, and does not apply any of the accepted lag periods that we have shown and discussed, let alone the longer one proposed by Dr. Roger Higgs. They also select a paper and use it as an example, as though one paper on the topic was ever submitted in the past. Try hundreds, and you could ask me to find just about any range of prediction within reason on a planet such as Earth, and I will find you a scientist that published it. It's just that simple. And their last line here is a beautiful piece of irony that will inevitably reveal their failure. The hottest decade on record, indeed, which only goes back to the 1800s in the mind of climate scientists, by the way, comes right at the end of the grand solar maximum of the Holocene. The last time the sun produced like this was the end of the last ice age and the start of the modern era. But on shorter time scales, the reliance on sunspots betrays them, as it does not at all paint a true picture of solar forcing. While sunspots, and indeed solar radio flux, peaked in the middle of the 1900s, we just recently reviewed that CME production, by measure of cosmic ray reduction, peaked around 1992. and did remain at high levels with low cosmic rays through about 2004. One of the reasons we say that the modern grand solar maximum ended around 2005, when the sunspots ended in that cycle. If you haven't seen some of the new data sets that the UN is going to be letting in for the sun, I have cropped just some of the key forcing factors here, and we see that the UV wavelength in the long wave, top panel, it does match the 11-year up and down of the sunspot cycle, but not the sunspot peak in the 50s. There was a high peak that occurred in 1960, but then the real peak was the 3 high cycles in a row in the 80s, 90s, and ending around 2004 or 2005. In the middle panel, we have geomagnetic activity, which excites dynamics and is related to Joule heating. And while sunspot cycles tend to push the dial to the max across the board, take a look at the gap from the 1950s to about 2005 along the bottom, the white, where the geomagnetic index never reached those lower levels as before. The peak of sunspots was merely the beginning of that geomagnetic maximum that would last 50 years. Finally, the high-energy protons at the bottom show how the solar flare energetic particle radiation was most prevalent in the early 2000s, half a century after the peak in sunspot activity. And so we not only have a failure to accurately identify the trends of solar forcing by a physics professor and a space science PhD, but they neglected basic solar forcing lag times that not even the staunchest global warming thumpers deny amidst the literature. These are 2 critical failures by the authors of that article. Not even to mention that when in the year 2000, NASA said we'd lost 10% of Earth's magnetic field in the last century or so, it didn't make it into climate models. And neither did the increased vulnerability of Earth when the ESA SWARM mission updated that to 15% in 2010, a number that is yet to be revised again in public reports. So, no, the sun's activity should never be measured with sunspots, and that is going away in upcoming climate models because the officials have realized the failure, and that after 40 years the solar physicists' voices had to be heard. Sadly, for the rest of us, interdisciplinary diligence to a Renaissance level is utterly absent in modern academia. And while some of the changes moving forward can be expected, others come out of the blue, like the recent focus on the floor of the ionospheric layers, the ozone, at the Arctic region. This layer just got vastly more important to discussions due to a recent work in Nature describing how ozone-destroying chemicals have resulted in half of the Arctic warming, which, by the way, is 1/3 of all global warming across the planet since the 1800s, and that takes the extreme focus on that plant food down yet another peg. But in addition to rewriting where they're pointing the fingers for climate change, this forcing pathway opens them up to even more influence to be discovered by the sun. The polar region is where the day-to-day solar forcing comes most into play, in addition to taking considerable particle forcing and electric induction during those extreme storm events that we've already seen. The solar particle forcing is very strong at the polar region, where for 6 months out of the year, there's basically no irradiance forcing at all due to Earth's tilt in the 6-month night. Their opening the door to this protective layer failure forcing pathway is exceptional, given that the interplanetary magnetic field surges protons to the northern polar cusp long before the CME shockwave reaches our planet. Here are some of the relevant portions of Professor Emeritus Dr. Brian Tinsley's talk from our 2019 conference, starting with that polar region and then moving across the global atmosphere.
So you'll recognize this diagram. Again, it's a north-south section through the Earth and its magnetic field and the solar wind. The main magnetic field in the Parker spiral is actually east-west, in and out of the picture here. And we've got these cusp regions where the field lines from near the magnetic poles there, considered open field lines, they map out and they can merge in with the solar wind in complicated fashions here and here. And then because the solar wind is moving relative to the Earth by 300 to 800 kilometers per second, the conducting field lines between these 2 points, a conductor moving in a magnetic field, are the sort that you have in a normal generator where you have an armature moving in a magnetic field and that generates an electric field which drives a current. So what we have is what's called a Lorentz electric field, but it's perpendicular to both the motion and the magnetic field. So now we have a north-south electric field, and that can be hundreds or so of kilovolts between these two ends of the conducting path. This is EZ, the Lorentz field. There's also a dawn-dusk electric field due to the north-south magnetic field. So we have an east-west electric field which drives these auroral currents that produce what's called the auroral electrojet, in addition to field line currents here. So there's a lot of complicated plasma physics going on there, but if you just measure the potential of the ionosphere above in the region of the south magnetic pole and the north magnetic pole, you can fly a satellite through it and look at the potential difference with respect to the low latitude regions, as has been done many thousands of times. And we find that there's a dip in that. There's a correlation, and if you look at the lagged correlation after 3 days, the opacity has dropped significantly at 95% statistical significance now for a couple of days, and then it starts to recover. Using as a reference 3 to 5 days before the maximum measured thunderstorm-generated global ionospheric potential change, we're measuring that at Vostok in Antarctica. Then there was an increase from 3 to 5 days before to 1 day to 2 days before to 1 day before, maximized on the day of the maximum of the measured electric field and decreased afterwards. So that's a confirmation, if you like, a control on the solar wind input having that effect. We also, sometime before, back in 2008, had published data on the surface pressure in Antarctica changing as the interplanetary magnetic field BY component changed. We did it on the basis of measurements at stations in Antarctica and in the Arctic. Mamie Lamb and colleagues did it in 2013, looking at a database of global meteorological data called reanalysis data, and then we're able to look at pressure changes all the way from the South Pole here up to the North Pole, and they found that the pressures when the BY changed from negative to positive in the solar wind, and it changes as the Earth goes through these waves in the heliospheric current sheet that Joan talked about. And there's a wavy structure, and you go from the southern hemisphere, if you like, of outward magnetic field to the northern hemisphere of inward magnetic field. And those waves, you go from a positive BY to a negative BY, which is the current direction in the Parker spiral, at least once in every solar rotation, so you have a 13-day periodicity, but you also have sometimes a 4-sector structure, and you have just 6 days one and 6 days the other, and sometimes it's a bit different again if there's a more complicated structure of active regions around the sun. Anyway, as you go from negative to positive, we found about 50 pascals increase in pressure over the Antarctic. There was a decrease in the mid-latitudes, southern mid-latitudes, because actually if you're increasing the pressure, air has to be flowing from somewhere to make that pressure change, and it flows from the lower latitudes. With Forbush decreases, which are decreases by 10 to 20% in the cosmic ray flux, or the big Forbush decreases, Todd and Kniverton, way back in 2001, showed that the cloud cover decreases by tens of percent in this region within the polar cap, which is where the lowest energy cosmic rays come in, which are most modulated by the solar wind. Now, cloud cover changes were observed by Pudovkin and Veretenenko here and with the Russian ozone observing network, and they found that cloud cover, or at least atmospheric transparency, decreased when you had Forbush decreases, which is saying that there's an effect on atmospheric transparency, which could be high clouds, cirrus clouds, or aerosol particles that changes as the currents change coming in during the Forbush decrease. With my student Matt Kirkland, we looked at how the solar wind speed actually varied as we went across the boundaries or magnetic sectors. Solar wind speed drops in the low speed region here, And the relativistic electron flux measured out at geosynchronous orbit also drops quite dramatically, actually, by several tens of percent. And this measure of the storminess in the North Atlantic, this is a global measure of storminess, and that dropped too, in synchronism with the drop in relativistic electron flux.
This is precisely what young Ferris Wald decided to focus on starting in 2016. He and his family had been following space weather and the solar forcing science, and Ferris had decided to do a science project on it. This is him at our 2017 conference in April. A few months later, he would win the New Mexico State Championship. Then months later, the National Middle School Science Championship. And in 2018, he made the top 100 in the Google World Championships. The storm forcing he revealed, using coronal hole streams on the sun, is uncanny. And if you can notice the little lag time of a couple of years that exists between the bottom curves, the solar input, and the top curves, the tropical storm frequencies, then you have been able to notice how this 16-year-old just figured out what those PhDs in the field could not.
This is a paper we published in 2013, but we've published another 4 or 5 papers since then detailing this. But I want to show that here we have these dots, various computer simulations of what happens to the collision rate coefficient, which you can see here is changing by orders of magnitude as we go up this vertical scale. And this is the size of the particles, so we go from a nanometer up to 10 microns. So we call this electro-anti-scavenging, which I think is occurring in these regions. So this is a summary, if you like, a flowchart of what's going on. On the day-to-day timescales, we see thunderstorms. This is our control. The thunderstorms change the global ionospheric potential, and we see changes in the Arctic and Antarctic clouds and the surface pressures. The solar wind drives polar ionospheric potential within the polar cap, and we see changes in clouds and, of course, in JZ. Cosmic rays also affect JZ and high latitude winter cloud. The relativistic electrons, solar protons, there's clear correlations found with JZ and atmospheric vorticity there.
The day-to-day solar wind forcing of the polar region, even outside of the extreme solar storm times, is certainly not some small, negligibly changing electrodynamic scenario. Apparently, half of Arctic forcing can account for a third of the world's overall climate change, and so even before the first study in the 2022 and beyond era is conceived, we've got numerous forcing correlations, mechanisms, and pathways for the forcing. We know some of the key model deficiencies and how the IPCC and major university professors are starting to see the writing on the wall and address those concerns. We've got the first steps to recognizing the breadth of solar forcing, even as the full particle influence remains elusive to the field at large. The future of solar forcing now looks as bright as the sun, and you are officially caught up on the last few years of climate science development that the news is conveniently forgetting to mention. Hopefully, that doesn't go for your professors as well. At the end of this examination, for now anyway, we remind everyone that we leave no quarter for pollution. This is the air we breathe, the water we drink, and the soil in which we grow our food. We can't poison it. But we also cannot confuse feeding it with poisoning it, and we cannot ignore the long-term implications of solar forcing of the terrestrial climate. More information is found below, including the entire series here, the full movie that came before, and whenever you're watching this, I'll see you in the morning for the daily update. Be safe, everyone.